Hi students, it's Miss Adams, and in this video we're going to learn about transforming data.
All right, so the effects of adding or subtracting a constant. If I add the same positive number, A, to or subtract A from each observation, what is it going to do to the different measures? So it's going to add a constant value, to or subtract A from measures of center and other measures of location. All right, so the mean, the 5-number summary value, quartiles, the median, the minimum, the maximum, those values are all going to increase or decrease by that constant. It does not change the measures of variability, so range, standard deviation, and interquartile range, okay, because all I'm doing is just sliding everything over. It does not change the shape of the distribution. All right, so if it was skewed right before, it's going to stay skewed right. The effects of multiplying or dividing a constant. If I multiply or divide each data value by the same positive number, let's call it B, it's going to multiply or divide measures of center and location. So the mean, the 5-number summary values are all going to be multiplied by that constant. It is going to multiply or divide measures of variability, range, standard deviation, IQR, by that constant. And it does not change the shape. So when I'm adding and subtracting, it only affects the measures of center, like the location values. It doesn't change the spread. When I'm multiplying or dividing, it does change the spread, and it changes the values, the location values. All right, suppose Mr. Tabor added 5 points to each student's test score. How would this affect the distribution of scores? So you can see I have these parallel dot plots on top of each other. I have the original and then the adjusted. So I added 5 points to everything, and you can see I took that dot plot and I just slid it over 5 units. All right, and then I have the summary statistics for the original and the adjusted. And if you look, X bar is the mean, SX is the standard deviation. We have minimum, quartile 1, median, quartile 3, maximum, IQR, and range. And the mean increased by 5. The standard deviation stayed the exact same. The median increased by 5. And the interquartile range stayed the exact same. So if I'm adding a constant, it's going to impact the mean and the median, but not my measures of spread. All right, adding or subtracting a constant. Mr. Tyson's class likes to do activities with M&M milk chocolate candies. Before one activity, Mr. Tyson handed out some candies to each student from a large bag of M&Ms. Here are a dot plot and a numerical summaries for the number of M&Ms each student was originally given by Mr. Tyson. The students were given one additional M&M of each color. Because there are 6 colors, the number of candies was increased by 6 for every student. Let's define the new variable as follows. Plus 1 of each color equals original number plus 6. What shape would the distribution of plus 1 of each color have? All right, so that new distribution would have the same shape as the original, which if I look at the original distribution, I can see that it is skewed left. All right, so it'd be skewed left with a peak at, I can see the peak before originally was at 23, but it's going to be at 23 plus 6, so 29 candies. Find the mean and the median of the distribution of plus 1 of each color. Well, I know that the mean was 20.464 before, and the median was 21.5 based off the summary statistics. So my mean is going to increase by 6, so 26.464 candies. And my median is going to increase by 6 as well, so 27.5 candies. All right, find the standard deviation and interquartile range of the distribution of plus 1 of each color. So if I add 6 candies, it's going to slide things over, but it's not going to spread them out more, okay, because the 14, the lowest value, is going to increase by 6, and the highest value is going to also increase by 6, so it didn't get more compact or more spread. All right, so my standard deviation is going to stay the same at 2.937, and my interquartile range would stay the same at 4.5. All right, suppose that Mr. Tabor converts his students' test scores to percentages. Because the test was worth 50 points, he multiplies each adjusted test score by 2 to get the student's score out of 100. So we just doubled it. And you can see the dot plot, how it changed when I doubled things, and the summary data. So you can see that the shape looks pretty much the same, but it's more spread out. Okay, you can see that like the actual dots are not right next to each other. There's more space between them. There's a wider range. You can see that the center definitely moved. Okay, so my mean doubled. It went from 40.8 to 81.6. My standard deviation also doubled. My median also doubled, and my interquartile range doubled. All right, so if I'm multiplying or dividing, it's going to impact measures of center and measures of spread. All right. Multiplying or dividing a constant. Here are a dot plot and numerical summaries of heights in centimeters for a random sample of 50 New Zealand students who responded to an online poll. Suppose we convert the heights of these students to inches. So remember that 1 inch is equal to 2.54 centimeters. I have the heights in centimeters, and I have the summary statistics for centimeters. What shape would the distribution of heights in inches have? Okay, so in order to change these, I would have to go from centimeters to inches, so I'd have to divide by 2.54 centimeters, but my shape would stay the same. Okay, so I can see this is skewed to the left a little with a peak at like 169, but I'm changing it to inches, so divide by 2.54, which would be 66.5 inches. Find the mean of the distribution. All right, the mean was 159.68 in centimeters, so I'm going to convert that to inches by dividing, and I get 62.9 inches. The standard deviation, again, I have to convert it to inches, so I'm dividing everything by 2.54, and I get 6 inches. All right. Putting it all together, so the numerical summaries for the midnight indoor temperature readings for a 30-day period are below. All right, and I'm going to convert them from Celsius to Fahrenheit. So these are in degrees Celsius. Degrees Fahrenheit is equal to 9/5 times the degrees Celsius plus 32. So find the mean indoor temperature in degrees Fahrenheit. All right, so I'm going to take the mean, and the mean is going to be impacted by multiplication and division as well as addition and subtraction. So I'm going to do 9/5 times my mean of 8.43 and then add 32, which gives me 47.17 degrees Fahrenheit. Calculate the standard deviation. Well, the standard deviation measures of spread are only impacted by multiplication and division. So I only need to worry about multiplying it by the 9/5. I don't want to add the 32 because that's just sliding it. It's not spreading it out more. So I get a new standard deviation of 4.09 degrees Fahrenheit. All right, which means the temperature readings typically vary from the mean by approximately 4 degrees Fahrenheit.
All right, thanks, and see you next time.